So what has been observed, and just quickly going through some of the major conclusions reached by IPCC in the fifth assessment in Working Group 1. The first is the observation of the warming of the world, and the reds basically mean warming of about 6/10 of a degree over the 20th century or more, 26/10 of a degree or more, and then the darker reds are even greater amounts of warming. And this is kind of what has led to the statement, a very, very famous statement now from AR5 about the warming of the climate system being just so uniformly pervasive all around the globe. I'm not going to talk much about precipitation in this talk. To go on, all right, the other major issue is accompanying the warming is a sea level rise. And this particular plot is showing in the center is a satellite estimate of the sea level change. And basically, it's rising in a lot of places, but not everywhere. There are some places where sea level change has been negative. And then on the panels above and below, the red line shows the global mean sea level rise, and the sort of wiggly curves are the local sea level changes. And you can see that there's a variation everywhere. Take Stockholm, for example, upper right. There's a lot of variation, but generally it's been increasing. You take something like San Francisco, it's a kind of much smaller variations, yet increasing. And then there are some places where ENSO affects a lot, like Pago Pago, where it's actually, there's a lot of biennial variation. And then Manila, where the local sea level rise is much greater than the global mean sea level. So this is something that is registered in the consciousness and minds of a lot of decision makers as we look forward to the rest of the 21st century. So I'm going to concentrate more on the future because I think the past is something that we now know well. We don't understand why it has changed, and we know a lot about it. So just go back a little bit. I went too far ahead. So how is the future going to change? Okay, so let me try this again. There's a delay. Okay, let's go forward slowly. Should I point it there? Okay. All right. So I'm going to talk about from the point of view of the climate research and modeling, where the basic thing is understanding and prediction. You want to understand, and on the basis of the understanding, be able to predict so that it's credible scientific information. And the principal aspects that I'm going to focus on are the weather and climate interface. That is, the weather events occurring on the background of a climate change, and to get regional information, because one of the things that policy makers want most is regional information, because the global information is already there, it's fairly robust, but what about regional information? So some of the questions that we can pose are, what is the trajectory of climate change over the 21st century? We know sort of the projections to 2100, but what is the trajectory between now and 2100? What will be the changes on a regional scale? And how can we better quantify the impacts, including extremes, caused by natural variations and force changes? Because this in turn has implications for impacts, particularly adverse impacts on ecosystems. So need a model, a mathematical model based on equations of the well-known equations of conservation of heat, momentum, dynamics. And this is kind of the Earth system model, where the changes in the Earth system that you saw on an earlier slide are, the equations for that are basically inserted into a model where you're separating the world into grid points, latitude, longitude, and vertical coordinates. And on the basis of this, there have been now these model projections from IPCC, AR5. You see on the left-hand side the two columns. The columns successively, as you go up, register the various scenarios, 2.6, 4.5, RCP 6.0, and RCP 8.5. And on the left is the years 2016 and 2035, basically roughly around the present times, or just shortly going to the present times. And on the right-hand side is the 2080 to 2100. So that's the end of the century. And you can see the most notable thing is, if you look especially on the right-hand side column, is the progressive warming that happens. The reddishness increases in the plot going from bottom to top. And you notice some other characteristics. The land warms faster than the ocean. The northern hemisphere, especially the polar regions, warms faster than the southern hemisphere. And the extreme north, the polar regions have an amplified warming. So, and on the right-hand side, the plot is showing you the warm days, and typically this is what leads into the concept of heat waves, and for the various scenarios. And for the red line, which is the RCP 8.5, the most aggressive scenario, the warming is 6 times, the heat waves are 6 times more frequent than what was probably in the 1990s. So there's a tremendous impact due to the general warming, which is a manifestation in the form of heat waves. And the IPCC statement was that very likely that heat waves will occur with higher frequency and duration as we go into this rest of the 21st century. Now, in addition to the global and regional warming, you have the warming of the oceans. And the plots at the bottom show, on the left-hand side, bottom plot shows the global sea level surface warming as a function of year, and the present is that vertical line. And so you see a rapid rate of warming, and these are results from different models. Basically, all the models agree that the rate of warming increases tremendously, even though they differ amongst themselves on the absolute value. And on the right-hand side bottom plot is the accompanying change in acidification, the pH change. So basically, the downward curve indicates, the downward slope of the curve indicates acidification is increasing as you go along with warming. This is all, of course, because of the CO2 increasing the atmosphere. The top 2 plots show the regional distribution in the year 2090 to 2099 relative to present. So it shows the increased sea surface warming that you get, basically yellows and reds everywhere, which means a warming. And on the acidification, basically the whole ocean is getting acidic, which has impacts on the marine ecosystems. In terms of Africa, this is a result from our model, which shows that the Africa as a whole has warmed by 0.5 to 1 degree centigrade, depending on the location, between pre-industrial and now. And then as we look to the 2100s, then the warming is an additional 3 degrees centigrade averaged over the entire continent. But this is still with a model which was fairly coarse, 100-kilometer grid size. So what we kind of want to step into is how can we make the tool more effective for getting us regional information? And one of the reasons why you want regional information is things like these, where you have floods occurring in some places, very localized floods, localized to windstorms, snowstorms, fires, droughts, aridity, and very heavy downpours. So this is all this is extreme events which occur or which tend to be noticed and perceived more on the local scale. So now you have to capture regional scale events and also the extremes. So the tools for exploring these have advanced substantially all across the globe in the modeling institutions. And what you're seeing here is the conceptual aspects of how models are advancing to capture this issue of both regional and the complexity, which means capturing the realism of the events. So you're marching down 2 channels where you're making the models go to higher and higher resolution so that you get more regional information on the one hand. On the other hand, you also want to capture the realism of the whole system, the climate system, the biogeochemical system, and that we call the Earth system complexity. And depicted in some of these plots that you see are actually manifestations of those. In the left, you see a high-resolution atmosphere model, and then you see kind of aerosol distribution simulated by a high-resolution model on the right-hand side. The middle panels denote sea surface currents and salinity with high resolution, and the primary productivity, which represents a complexity in the Earth system. And then that kind of cascades into results, which are kind of the outcomes of these climate extremes, like the severity of summer heat waves, sea level rise, and then the general warming of and cooling of the atmosphere, depending on where you're in the troposphere or stratosphere. Now, one point that I want to make is the resolution of the models, because that's kind of what will get you regional information. So I'm going to show you 4 slides in succession, and you're going to have to guess what it is that I'm talking about here. This is a famous historical site. Let me give you a clue about that. So any guesses what this is? This is at the resolution where the models were essentially let's say about 4 to 5 years ago. They were robust models, good physics, good chemistry, et cetera in them, but the resolution was not good. Even though the results, broad results, might be very acceptable, the resolution was not good. So anyone guess what this is? Okay, here you go. Better? Any better educated guess? Okay, that's what it is. The Great Wall of China. And this is what you want to capture. And fortunately, with the advent of high-performance computers, we have been able to probe into this frontier, not perhaps to the degree of satisfaction that still a regional a lawmaker interested in regional decisions would be happy with, but nevertheless, we are getting there. You can see the cost of these things. Okay, so this is what actually comes out of some of the advances we've made. This is actually a 12.5-kilometer global atmospheric model, and you can see, and what it's showing you is condensed water in the atmosphere. So it's showing you clouds and cloud distributions in actually very great detail, much better detail than 5 years ago. And with this, we've actually, so I'm going to show you some results that we have obtained with this, and you can see what resolution does and convince yourself that it is actually credible. The top left is the observed annual mean precipitation over North America. So you can see the features where the western side of US is mostly dry, excepting for the northwest part, and the sort of eastern coast is more wet, and the wettest regions are in the southeast. That's the observation in the top left. And you go to the top right, that's the model, as it says, vintage 2006, so it was built about 10 years ago. Then the model in the lower left is vintage 2014, so it was constructed 3 years ago. And then the latest model that we have is the 2015 version, which is in the bottom right. And you're going to see some animation with that model later on at the end. But this is a 16-mile tile, so that's about 25 kilometers global. Pretty expensive to run, but you can see the result. You can compare the top left and the bottom right to see how sort of vivid the capture is of the dry regions and the wet regions of the precipitation areas. Still not perfect, but nevertheless, you are getting information now at really county levels, which is proving very useful. Another example is this. Now, there are 2 plots here. There's a top panel and the bottom panel, and the bright red area is where there is a deficit of precipitation, and the blue areas are where there is more precipitation than in the red areas. Now, do you want to tell me which one is the model and which one is the observation? It's so close. So there's actually some dividends to be reaped from this kind of excursion into the advancement of resolution in models. Then another area that we've been recently exploring in is, especially because we're in Africa, this is very relevant, is dust and hurricanes. There's a lot of knowledge gap about what really happens, because dust storms are very prevalent, or about at the same time when hurricanes are forming off the west coast of Africa and then swinging towards across the Atlantic. And what is the interaction between them? This is still a question, remains a fairly unanswered question, and certainly the quantification is not there. But with the high resolution models, you can actually capture both the dust, lofting of the dust into the atmosphere, as well as the formation of hurricanes. And you're going to see both in some animations to follow. So now we are going to go into to see three animations. Let me just describe what they are. The first animation, these are very short movies. The first one is going to show warming over Africa, starting from historical period, which is roughly 1860 to present time. Present time is about 2010. And then projections to 2100. And we're going to see effect of two projections. One is the RCP 2.6, which was at the time of the AR5. It was the one with the most aggressive mitigation strategy. And then RCP 8.5, which was the least aggressive emission strategy, so very high CO2 and so on. And accompanying that comes the second animation, which is going to show you changes in surface ozone. Now, it's interesting that the chemistry, atmospheric chemistry also, I mean, other than the CO2 one, also undergoes some very severe transformations because of the emissions of other gases also increasing, and that affects, in particular, ozone formation near the surface. And the third one you're going to see is the capturing of regional complexity. As I mentioned earlier, the dust transport, and particularly in a region where we are right now, the lofting of dust into the atmosphere from these regions creates not only local pollution, but also very broad-scale intercontinental transport of pollution, of dust aerosols. So with that, we can go to the first movie. So the years are marching on the right-hand side. You can see Africa, this focusing on Africa, so Africa is warming. As you're going up, coming up to about 2006, and then it'll stop briefly. So the redness is just exacerbation of the amplifying of the warming. And now you're going to see on the left-hand side the RCP 2.6, and on the right-hand side RCP 8.5. And these are absolute values of temperature. And the right, obviously, will be getting more redder earlier than the left. And basically, this is a resolution which captures the regional features. Even though this is actually a little bit older model, it does capture the regionality very well. And now we can go to the, oh, well, there's still some more left. So it's showing now the rest of the globe, and there's sort of warming happening everywhere. The tropics, though, are warming more. The tropical land areas are warming more than mid-latitude areas. Okay, I think we can cut to the other movie. So now this is going to be the ozone, surface ozone. And one thing to remember is when you see the bar on the left-hand side, the Environmental Protection Agency in the US usually has a value of about 65 parts per billion by volume, which is the left scale. They're almost the top end of the left scale. That's kind of where, if it exceeds that, it's fairly unhealthy. And so you see that, it's not exceeding that much till now, but now you watch as we go into the future, that especially 8.5, because of very large increase in methane, so this concerns methane, you actually start to see a lot of increase of surface ozone in these simulations. And biomass burning is the prime contributor, plus the level of development activity, the level of increase in population gets you these red areas over Africa, which is kind of a little bit of a surprise because they're used to more industrial areas in the north getting this increase in surface ozone, but actually it happens in Africa too. So there's an atmospheric composition and air quality issue, which also is coming in along with the surface warming. And now the third movie is going to show you dust. Now this is a movie where it's going to go through a whole year, which is on the bottom left, so it's starting in January. And what it's capturing is tagging dust emitted from different land areas in Africa. So it's just kind of focusing on dust, natural dust, lifting and transport. So the amount of dust that is lofted from each area depends upon the aridity of the area. So it depends on the rain and precipitation history over the previous years. It depends on the topography. The more the slope, the more sort of the lofting of dust, and of course surface wind speeds. So using all that information, in a model which has meteorology going on, you can see the dust getting lofted. Now, what's interesting is so there's a local effect of the dust. There's a lot of local dust. When sandstorms occur, the skies here, for example, in these areas are quite full of dust. But equally important is the transport of the dust across the Atlantic from these different areas. Almost throughout the year, with sort of varying proportions, and depending on the prevailing winds, you can either go towards almost even up to maybe well into South America to then Central America. So you have quite a range of transfer of dust from various sources. So this is also another, I was talking about atmospheric composition and air quality earlier. So the fact that we can tag these dust, or for that matter, any aerosol particle from different places means that you can actually start to ask questions about air quality being affected by what, from where. You can actually deduce that using this model, because now you can resolve these regionally. You can do the regional meteorology very well. And so this is just looping around. So I think, let's see, I will conclude there. And now we are going to get a remote speaker in on the line. So are we ready to? So our next speaker is going to be Dr. Alyssa Ocko, who's going to be calling in from, it's Alyssa, not Michael. Michael is next. Sorry, Michael. So Alyssa is a climate scientist at the Environmental Defense Fund in New York. And she works on the climate impacts of long and short-lived species like greenhouse gases and aerosols. And she comes in from the point of view of giving a scientific perspective to people who want scientific guidance into climate-related policy decisions. And she's also she enjoys communicating science to non-scientists. So with that, Alyssa, the floor is yours, or the medium is yours. And I will advance the slides. Just tell me next slide, and I'll do the advancing. So go ahead. It's all yours.
Great. Thanks, Ram. Can you give me a thumbs up if you can hear me? Can you hear me?
Yes. The answer is yes.
Great. Okay. So thanks, Ram, for that introduction. I'm really happy to be here, even though I am across the ocean. And so I'm just going to give a little bit of insight into the climate change impacts that have been happening all over Africa, and also what we expect to see in the future. So not too long ago, climate change was considered distant. It was distant in that its impacts were far away, but it was also distant in that its impacts were in the future. But as we all know, this is no longer the case. Scientists have already observed impacts of climate change on every continent and in every ocean. And the figure on this slide is taken from the IPCC AR5 Working Group 2 report and synthesizes our current knowledge of climate change impacts. So the IPCC has categorized these impacts into physical changes in blue, like ice melt and sea level rise, biological impacts in green, like changes to ecosystems, and societal impacts in red, like threats to food production and human health. So there are several other layers of information on this graphic, but I mainly want you to focus on how these impacts are spread across the entire world. Next slide. So Africa is clearly no exception. This figure is an adaptation of the previous one, and the circles with white icons represent a major contribution of climate change, and the colored borders represent scientists' confidence in attribution to climate change. So you can see that all sorts of impacts are plaguing Africa, many of which have major contributions from climate change and considerable confidence in this attribution. So now I'm going to go into a little bit more detail on what some of these observed impacts look like across the continent. Next slide. Okay, so in the latter half of the 20th century, for example, the lack of rain and increasing dryness of the Sahel led to 1 in 6 trees dying and 1 in 5 local tree species disappearing. The decline in fruit-bearing trees is especially concerning because fruits are a major source of food, nutrition, and income. Another big source of income is coffee. In Ethiopia, 700,000 families depend on coffee production for their livelihoods, and coffee yields in Ethiopia have declined by 35% between 2002 and 2009 because of widespread infestations of a beetle due to rising temperatures. Flooding has been a huge issue in North Africa in the 21st century. Sudden, massive downpours have led to thousands of mortalities, millions of dollars in economic loss, displacements of hundreds of thousands of people, destroyed agricultural lands, food insecurity, and loss of shelter. Even in South Sudan, refugees residing in a United Nations camp in 2014 were living in knee-deep, sewage-contaminated floodwater, forcing some families to sleep standing up so that they could hold their children from being in the water, to keep them out of the water. Now, South Sudan is plagued by a severe drought, causing a food shortage, and the World Food Program estimates that nearly 5 million people, which is 40% of the country's population, are going hungry. Both long-term changes in rainfall from climate change and El Nino have caused one of the worst droughts in recorded history in this area. And the drought in East Africa has also exacerbated already existing international conflicts, such as water security at the Ethiopian-Kenyan border and food security in Nigeria, sparking political instability. So another food insecurity issue is due to reduced fishery production in the African Great Lakes and other lakes in the area. So fishing in these lakes is a critical source of income for around 1 million people, and lake fish account for up to 40% of the animal protein supply for nearby communities. As a result of temperatures in the lakes warming by around 1 degree Celsius over the past century, biological activity in the lakes has considerably declined, threatening the fishing industry. Livestock in Africa has also been impacted by recent droughts, with mass deaths from lack of water and heat stress. And as temperatures rise, disease-carrying insects are spreading their territories to higher elevations, threatening communities that otherwise are able to avoid diseases like malaria. And finally, contributing to water stress in Africa are retreating glaciers and wildfires. While deforestation is considered the main cause of Mount Kilimanjaro's shrinking glacier, frequent wildfires on the mountain have been attributed to rising temperatures from climate change, and they've destroyed an area of forest on the mountain that is comparable to the size of the Palm Oasis right outside of Marrakesh. So that's a large area. And so the forest on Mount Kilimanjaro is actually really critical to water security for local communities because the trees take in so much of the water from the clouds and feed the rivers. So the amount of dew lost from the decline in forest area over the past 40 or so years is equivalent to an annual supply of drinking water for around 1 million people. Next slide. So unfortunately, these impacts are only expected to get worse with future warming, as we all would expect. This figure here consolidates information in the IPCC AR5 Working Group 2 report on future. And so for each factor in each region, there's a little up or down caret or a tilde, and those stand for increasing, decreasing, or trends staying roughly the same. And so the more carets, the stronger the signal or probability. I didn't want to show all of the legend information because it's quite overwhelming, and then the text would just be really small on the screen. And so what you can see from this figure is that in the future, we expect average and extreme temperatures to increase across the entire continent. Changes in average rainfall and drought are regionally dependent, so they vary quite a bit depending on where you are. We see the strongest reductions in average rainfall in Southern Africa, along with increased chance of drought. And extreme rainfall is expected to increase in East Africa, along with reduced chances of drought. So sea level is also expected to impact all the coastlines around Africa. And so these changes in climate conditions will undoubtedly further impact societies and ecosystems in Africa, but quantifying the risks of impacts is not easy. And that depends on uncertainties in our decisions going forward, such as the amount of greenhouse gases that we emit in the future, but also uncertainties in our understanding of the climate system. Next slide. So we employ global climate models, of which Ram discussed earlier, to understand what sorts of impacts we may face. So for example, this figure is taken from a recent study that looked at how areas in Africa suitable for key crops may change by mid-century. So the study used 5 different global climate models and looked at an emission scenario in which the world continues with business as usual, which means that we continue to emit a lot of greenhouse gases over this next century. And so these 9 agronomic crops are considered critical for food security. And so you see what these figures are showing is the changes in areas suitable for the crops based on what's suitable now and then compared to what will be suitable in mid-century. So green are areas that will be more suitable for that specific crop, and then the red colors are those that you decline in areas suitable for growing these crops. And so the models here show that the common bean is highly sensitive to climate, and around 90% of currently cropped maize area is projected to experience negative impacts. However, the projections also suggest that opportunities may arise as some crop suitability areas expand into new territories. So that's the green color. So this applies to the cassava in South Africa and the yam in East Africa. And East Africa in particular may have further opportunities for bananas and groundnuts, millets, and cassava. So overall, these types of model simulations are extremely valuable because they provide a lot of information for decision makers, as Ram was talking about earlier. So first, by seeing a snapshot of the future, we understand what we are working to avoid when we develop plans to reduce emissions of greenhouse gases. But second, we are learning how to prepare for the future and adapt to regional changes if these projections come to fruition. And third, we are also learning where other opportunities may lie so we can prepare to take advantage of new situations. So for example, if we know now that a certain part of Africa will become much more viable for growing a certain crop, then we can start cultivating that land now and understanding how to transition our agriculture so that we can make use of that land, which may become more viable for that certain crop. Next slide.
You're going to wind up a little bit sooner than you think.
What's that?
I guess you'll have to wind up so that we can get Michael an opportunity also.
Got it. So I just wanted to mention that even though this sounds pretty depressing, there's a lot of adaptation experience in Africa that has been significantly growing. And so there are all sorts of local and national plans and policies that are emerging. And even though there are challenges to deployment of these plans, there are strategies in place to address those types of barriers. And so this slide is just, and this image is just one example of plans that are in development to take all of the new climate information that we're getting, especially from climate model outputs, and put that into use to really make people aware in these regions of what's going on and what may happen in the future so that they can plan accordingly. And I'll end there. Thank you.
Thank you, Lisa. We will go in for questions later on after Michael finishes. So our next speaker is Michael Oppenheimer, who's the Albert G. Milbank Professor of Geosciences and International Affairs at Princeton University. He also heads a program called STEP, which integrates science, technology, and economics and into environmental policy. And he's worked extensively with IPCC, and particularly on providing the scientific information analysis for climate adaptation and mitigation. So, Michael, the floor is yours, or the medium is yours.
So thank you, Ram, for inviting me here, and thanks to Alyssa for giving me such a clear setup for what I'm going to talk about. In considering climate impacts, recently there's been a lot of research on the next question that follows, namely, what's the human response to those impacts? As Alyssa mentioned, there are options to adapt to these impacts as they play out, and in fact, in anticipation of the impacts in advance. The question that we've started to look at some years ago at Princeton is what's the likelihood that humans would move in response to climate change climate changes that are unfavorable to their current existence or their current livelihood. So for instance, in the case of agriculture, particularly in Africa, many people are dependent for their livelihood entirely on their ability to cultivate land. And with the changes in crop yields that Alyssa discussed, where we see losses in yields of beans, maize, and sorghum in South Africa, which is going to be the particular focus of this talk, one would be interested next in the question, so what do farmers do in response? Do they stay? Do they look for other ways to earn a livelihood? For instance, move into some opportunity aside from agriculture? Or as it does occur in many cases in many countries, do they pick up and move to another place where they have a better chance to earn a living and to thrive? I want to point out that this kind of decision pervades the responses to climate change. It's true of responses not just to agriculture, but to sea level rise, to extreme heat, and probably across the board. So let's look at the next slide. This slide just merely demonstrates the magnitude of the effects on South Africa in terms of changes in mean precipitation and temperature. This slide has a slightly different presentation than usual. It's the predicted changes per degree Celsius of global warming, and this comes out of the IPCC's fifth assessment report. And you'll notice that with regard to changes in temperature in the upper panel or changes in precipitation in the lower panel, that South Africa is kind of a bullseye area for the direct impacts, the physical impacts of changes in the climate system. Let's look at the next slide. Our expectation, of course, is that those changes are going to have effects on yields of some of the major crops, as Alyssa pointed out, some negative, probably some positive. And we see on this slide the results from two different types of impact models on what in particular would be the effects on maize yields. So we see in the top row the results of what are called a process-based model. This is sort of analogous to the climate models, which are process-based, which have the basic physics and chemistry of the climate system embedded in them. In this case, we're talking about basically physiological processes which allow us to render the responses to crops. And this is a moderate emission scenario, which is essentially RCP 4.5. In each case, the left-hand column is the current yield. The middle column is the future yield in 2055, mid-century, and the right-hand column is the difference between the two. The lower set of panels is what's called an empirical model. That is, lately there's been a lot of progress in the impacts business in inferring future changes in crop yields by looking at responses to past climate variability and making certain assumptions about how that would translate into the future. There are, among other benefits of this type of modeling, is it probably captures some degree of climate adaptation. For instance, in the past, farmers would have, of course, in some cases, shifted crops to the ones that, as Alyssa mentioned, might respond positively to climate variability. So we capture some of that in models that use past variability to project into the future. Let's now look at the next slide, please. So on this slide, we see a rendering of South Africa itself. And this sets up the framework for inferring what changes in migration look like based on past climate variability. That is, we have experience, we have good data sets for precipitation changes, for temperature changes, and for migration internal to South Africa among the various areas, which are divided into about 50 some odd what are called council districts. So in the upper left-hand panel, you see changes in precipitation that occurred in the year 2011 compared to the baseline. And the next one, we see anomalies in maximum temperature, and each of these broken down by the council districts. And then at the bottom, we see migration that occurred during the same period out of each of the council districts. This is gross migration. It does not account in this case for people who might have been migrating from one council district into the council district. So this is just migration out of each council district. It's worth noting that for South Africa, internal migration is essentially the whole migration story, that compared to internal migration, there's very little migration to other countries. And again, I want to emphasize what we're talking about here is the measures that people take to adapt to a change in their livelihood, and they could adapt locally, they could migrate, they could change jobs, they could fall into conflict. There's a lot of literature now on conflict, and what we're trying to do here is infer what the responses are to changes in past climate variability in terms of migration. So let's look at the next slide. And well, you can make these inferences by constructing a statistical model and try to infer the sensitivity of migration rates to past variability in precipitation and temperature. So we looked at about 20 years of data, 15 years of data. We looked in 5-year periods because that's the resolution of the census data from which information about what people actually did, how they migrate is drawn. We build a statistical model for migration in response to temperature and precipitation variations, and we control for other features, which, for instance, might also affect the tendency to migrate and might complicate the data. For instance, you get bigger numbers for migration out of areas that might be hotter anyway, or out of areas that have higher populations. So you have to control for those factors. And as we said, we use 5-year averages. And this is all done against the background of a country which is a fairly large amount of internal migration anyway. Over the period, for instance, 2007 to 2011, about 2.5 million people migrated internally. And the results are quite interesting. For each 10% change in the positive direction in anomalies of maximum temperature, you get about 1.9% increase in the migration rate. And similarly, for negative changes in precipitation anomalies, you get about 2.2% change in the migration rate. So there's a significant, detectable and statistically significant change in migration in either in response to either temperatures that are getting too warm or for precipitation conditions which are getting too dry for agriculture to proceed at the optimum. And we also see, although I'm not going to show those results, a related change in agricultural employment in these districts. So it's fairly clear that the reason people are migrating is not simply due to it's too hot to want to live in these districts, but it's in a result specifically to opportunities for gaining livelihood and employment in the agricultural sector. I will say we've done much broader studies, not only in other countries, but with a very big OECD data set, which comprehensively shows effects of international migration from basically all countries around the world into OECD countries. And we see the same effect of increases in migration rates that are driven by climate variability and modulated by the effect on the agricultural sector. And taking all this evidence together, it implies that for the sorts of temperature and precipitation anomalies that we expect to see in the future, that there will be substantial increases in migration, all other things being equal. All other things won't be equal, but if you assume the world otherwise remains more or less the same, one expects, particularly in certain areas like perhaps across the US-Mexico border, or the area of people moving from North Africa into into Western Europe, that one would expect to see substantial changes in response to climate change. And in conclusion, I want to just say that the point of such research isn't simply to create another worry, but to give governments an idea of where changes in migration flows could occur, and in that way give them an opportunity to consider policies either for managing those flows by encouraging them under certain circumstances and being ready, the recipient nations being ready to receive the migrants, or in other cases, discouraging the flows by the countries that might otherwise lose the migrants, availing themselves of opportunities to improve the livelihoods of people and thereby encouraging them to stay. Thank you.
Okay, I'll just wind up here with just a summary. What we have discussed here is advanced scientific tools for going beyond the results of the previous, let's say, the IPCCs, getting into more regional aspects, getting to talk about frequency of occurrence of extremes that could be hurtful and harmful, and talking about capturing the realism of the system so that the information is more credible. And these are some of the issues that arise: ocean heat content, sea level and coastal inundation, atmospheric composition changes, weather extremes superposed on climate changes, and consequence for human systems and ecosystems. And how these tools can actually then help in the kind of analysis that Elissa and Michael talked about, which are informative information to policymakers, actually provide the scientific translation or translation from science into guidance for educated guidance for policymakers. And I'm going to end this with another animation, which is going to show you a simulation of tropical cyclones in a global climate model. Now, when you go to high resolutions, you can actually imagine capturing these very, very extreme events where you're talking about very high wind speeds, very localized phenomena. And as you go to high resolution, our desire should be to capture those events. So this is a 25-kilometer global climate model where actually you can see category 3, 4, and 5 hurricanes being simulated. That is, the wind speeds that you get in a hurricane are simulated. So the simulation is going to show you the sort of latter half of the year. So it's going to show you the Atlantic cyclones and hurricanes forming and the typhoons in the Pacific. So what we're going to do is let the movie roll on, and as the movie rolls on, we'll take questions. So Tom, thank you very much for everyone for the attention. So we can roll the movie. We can start.
It's not on. There we go. If anyone has any question, please raise your hand. We'll ask some questions for not only Ram, but Dr. Elissa Acko and Dr. Michael Oppenheimer.
I'm from South Africa, so it's a little bit sobering to watch what's been predicted. But is there any scenario that you could see the world taking that could help us to avoid those things? Or could you name a number of drastic enough things that would have to happen in order to avoid the scenario that's been predicted from all the speakers?
I'll let Michael take this, but I'll just maybe preface it by saying that 8.5 obviously is something that we would want to avoid. That kind of has all the hallmarks of lots of extremes occurring. 2.6, it was chosen as the one which was in the IPCC AR5 times as one of the sort of the least aggressive paths towards high emissions. But even with 2.6, that the occurrence of extremes is not necessarily precluded. So even that might be, it's much less than 8.5, of course, but even 2.6 is not without its effects. Maybe I'll let Michael amplify this more because he's studied the impacts in South Africa much more than I have done. Michael, are you on the line still?
Yeah. So remember that the governments have aimed at a warming of less than 2 degrees globally and aspirationally 1.5 degrees. And RCP 2.6 corresponds more or less to a stabilization of the climate within this century of something like 2 degrees. So it's a good surrogate for the current objective under the Framework Convention. Now, that's a lot more manageable world than an 8.5 world. And, one thing you might say on the plus side, it looks like if countries do what they agreed to do under the Paris Agreement, that 8.5 would be clearly avoided. But nevertheless, even with diligent efforts, RCP 2.6 will be difficult to achieve, but with focused effort, it could be achieved. But even under 2.6, there would be substantial adaptation that would be necessary. It's just that it probably would minimize, such an objective would minimize the damage globally, but it would not be without costs. But, my personal view is that with focused effort, we can get to these minimum emissions trajectories, and that they would give us a good chance to thrive in the future. Although adaptation is going to have to become a bigger and bigger part of policies that governments consider.
By the way, the red circles there are the category 4 and 5 hurricanes forming. So, yeah, go ahead.
My name is Thomas Kraneis. I'm coming from the Association of Consulting Engineers from Germany. The results which you have shown today, they are known to your American insurance companies?
Yes, I mean, this is all results in the public domain. So yes, they are known, excepting you see that it's written prototype. So this is not yet a prediction model, an operational prediction model, but it is a tool which is, you can regard it as a stepping stone to an operational prediction model. So there are older versions of this model which were not at such high resolution, which actually the insurance companies are using, or models like that they are using for their own purposes.
Well, I think with your prediction, we shall sell our shares of the insurance companies, because it makes no sense. They will be in a few years going in bankruptcy.
Well, there are several, I just urge a little bit of caution about thinking on this, because this is just a model so far. It is going to be, first of all, even this kind of model has to be vetted more. It has been vetted in the sense, there are peer-reviewed publications, but beyond that, it really has to be solid in terms of how people view it in a regular sense, in a regular operational sense. I mean, before it becomes operational, you have to verify so many cases, which depends on things other than the model. It depends on data quality control. It depends on initialization of the model. So there are a lot of factors still in play, and I kind of wouldn't want anyone to rush to a conclusion that this model is ready to be deployed on a forecasting an actual event, because that kind of is another big step in and of itself. So I don't think the insurance companies will go bankrupt very soon. But you know what? They have all the information to construct such models themselves. All this is in the public domain. So conceivably, they might actually be ahead of the science community in building such models.
We have time for one more question. If there's no questions here, I'll ask one. Regional predictions and climate models, obviously not all regions are equal in terms of the skill of these models. Are there certain areas where you see certain features better predicted, or certain areas where there's still some uncertainty associated with impacts?
One of the most remarkable, thanks for asking that question. One of the most remarkable things which the scientific community still is, I think, not able to properly answer, but it's a remarkable thing that Atlantic hurricanes, actually, if you give the conditions in July, and Atlantic hurricanes mostly are in the sort of July to November timeframe, if you give the large-scale data as of 1st of July into these models, not only this model, but there have been other models too which have shown this, the rest of the hurricane season actually predicts very well the number of hurricanes you're going to get over that season. That is the frequency of occurrence. So that's not enough, but it's one of the characteristics you do want to know. And why it happens is actually boils down to this has been chased down to two simple physical reasons. One, the degree of warming of the tropical sea surface temperatures over summer near the African coast is very important. It's a very important determinant of whether hurricanes are going to occur or not. But that's only one part. The second part is vertical wind shear. That is, how are the winds distributed in the vertical and what's the gradient in the vertical. Somehow, those two factors are the principal factors in determining, is there going to be a lot of hurricanes in the season or very few? And now, going beyond that, you want to, of course, know the landfall, how many hurricanes which form do affect land. And that actually is also beginning to be, successful to some extent. That's not the story with the Pacific. The Pacific seems to have other factors determining it. So there are some skills in some areas. This is very marginal, you may think at the moment, but 10 years back, we weren't even in command of these things. So as we kind of probe these models more, we are learning more about skills. But there are some areas which may be a long time in coming in terms of understanding. So I hope it answered your question. I don't know if Elissa or Michael wanted to have a quick word in here about this particular aspect. Elissa? Michael?
Is that the?
Michael?
Yes, it's a question about predictability at the regional level.
Right,
Is that
in different regions.
Yeah. So from the impacts point of view, we're certainly getting to the point where the increased resolution in the models has made it easier to have more and more refined projections of what we can expect. On the other hand, it's a very difficult matter. Going that next step from the climate changes to the impacts introduces lots of complications which are so specific to particular regions, because you have essentially the socioeconomic system that you have to get into the modeling at some point, that judging the human response, it's going to take us some time before we can fully implement all the improvements in just the physical part of the climate models without even mentioning the more complex socioeconomic system. So we'll get there, but it's going to be, years or decades, perhaps.
Elissa, do you want to have a quick final word on this?
I work at the Environmental Defense Fund, and so we do a lot of environmental advocacy work and climate models, and just watching them evolve over time and get better and better has just been such an amazing tool to be able to use in the climate policy and decision-making world. And so it's been really cool for me as a young early career scientist to even just see how they've been able to develop over the past 10 years to a place where they're at now. And it's really promising in the future in terms of taking all of these results and putting them into action. It's really exciting. And I definitely encourage you to learn more about climate models and their use as tools as we go forward.
Okay, thank you, Elissa. Thank you, Michael. And thank you, everyone, for staying around. It's a pleasure talking to you.
Can we have a round of applause for our speakers, Dr. Ram Ramaswamy, Dr. Elissa Acko, and Dr. Michael Oppenheimer. Thank you very much. Now, we still have